For question number 13, and we are about to start with this is the paper code 65, sorry, 3116 or 3161, sorry. So this is a paper code 3116, and this is the first subset of that, and we are going to solve one in the physics part. So this is for the physics part. And in the following diagram, we're showing dispersion of white light by glass prism. The colors P and Q are represented as, and we know that the acronym for the colors is WIBGYOR, which is violet, indigo, blue, green, yellow, orange, and red. That is dispersed by the white light. So this P is V and Q is R. So our option is it's asks the colors of P and Q. So that means it's B. So this is option B. Let me show you how the dispersion happens when light passes through a glass prism. So this is the incident white beam of light, and it was supposed to go like this. So it was supposed to go like this, but because the different angles bends at different colors, so it was supposed to go like this. So I'm going to make this a dotted line. And because different angles bend at different colors, so here the dispersion takes place. So it's the constituent seven colors gets dispersed into, so this is one, two, three, four, five, six, and this seven. And if I place a screen here, so I will get a spectrum that is a band of seven colors. And we remember those seven colors by the acronym WIBGYOR. And we have to write there WIBGYOR from here. That is from downward to upward. So downward, upward. So this is white, indigo, blue, violet, indigo, blue, green, yellow, orange, and there is one more which is red. So this is red. Now the least bent color is red, and the most deviated from the original path is the violet. So this is P and this is Q. So this is violet and red. Moving on to the next question. Okay, for next question, that is question number 15, we have to uh, choose the option for the magnetic field inside a long straight current carrying solenoid. Okay, so for the long straight, what is a long straight current carrying solenoid? It is a insulated copper wire wrapped closely in the form of a cylinder. So this is a long current carrying solenoid. And inside the solenoid, the magnetic field is in the form of parallel equidistant arrows, and this is the magnetic field inside, which is parallel equidistant arrows, and they emerge from one pole and merge at the other pole. So they emerge from the pole, the end which is called north pole, and they merge at the other end. This is merging here. Okay, this is the pattern of the magnetic field, which is exactly the same as the pattern of the magnetic field lines inside of or for the bar magnet. So here it's merging. So magnetic field lines are merging here. So this is the direction of the magnetic field lines, and this becomes the north pole where it merges, and this becomes the south pole. So from where the magnetic field line emerges, it's the north pole, and where it merges, it's the south pole. Now inside, if you see, these are the parallel set of equidistant arrows, and this represents, so this area, this represents the uniform magnetic field. So this is uniform magnetic field. And uniform magnetic field means that the magnetic field is same at all points. So this is the uniform magnetic field represented by the parallel set of arrows, and uniform magnetic field means that the magnetic field is same at all the points. So whatever point you take inside the solenoid, so magnetic field is same inside all the points. So D is the correct option for this one. for question number 15. Okay, for question number 16, question number 16, we have to, this is question number 16, and it's asked in human eye, the part which allows light to enter into the eye is the cornea. So this option is option D, because if this is an eyeball, so which part allows the light to enter? This is the eyeball, which has a diameter of approximately 2.4 centimeter. Yeah. And this bulge out part is called cornea. And the light enters through this part. So our option is option D, which is cornea. Okay, for question number 24, it's given that let the resistance of an electrical device remains constant. So resistance is given by R, which is constant, and there is an electrical device which is connected in the circuit. So R is constant, while the potential difference across resistance decreases to 1/4. So when the potential difference is denoted by V, we know that V is equal to IR, and the value of the current is now V by R. Let this be equation 1. Now it's given that potential difference decreases to 1/4. So then now what the new potential difference is V dash, which is 1/4 of the original potential difference, which was V. What will be the value of the new current? So new current will be I dash by V dash by R. R is constant, so this is V dash. So V dash is now, that is the new potential difference is V by R. I dash is a new current. We are using the Ohm's law. So this is, so for new current is no new potential difference, and the resistance remains constant. New potential difference is new potential difference becomes 1/4. So this is 1/4. So that means V by 4. So V dash is 1/4 and R. So this becomes 1 by 4 into V by R. Now V by R is the original current. So that means the current is now, the new current is 1/4 of the original current. So what change will occur in the current through it? So we can write here that current becomes 1/4 of its original value. So I'm going to write here current becomes 1/4 of its original value. Okay, so this is the answer for the first part. Now, we have to state the law which we have used. So state the law which helps us in solving the above stated equation, and the law is Ohm's law. We have to name it and we have to state it. Means we have to write the definition. So this is Ohm's law, and this law, it states that potential difference, which is V, and potential difference across the ends of a given metallic conductor or the wire is directly proportional to the current flowing through it. Definition is not yet complete. We have to write the condition provided the temperature remains constant, and that's a very important condition. Provided the temperature, it remains constant. So if you have to mathematically write this, this is V is directly proportional to I. And if you remove the proportional, there is a constant which is R, and R is the potential difference. Sorry, R is the resistance. So V becomes IR. So we have used this to find that current becomes 1/4 of its original value. So this is how you have to answer this. Moving on to the next question. Okay, for question number 25, a light ray enters from medium A to B. So this is medium A and this is B, as shown in the figure, and we have to state which one of the two media is denser with respect to other medium. So when light ray enters from medium A, so this is medium A and this is the refracting surface, which is refracting the light when it goes from medium, and this is actually the normal that is perpendicular. So this is normal. Now the angle between this is the incident ray. Now the angle between the incident ray and the normal is the angle of incidence. And the angle between the normal and the refracted ray, this is the refracted ray. So this is angle of refraction. So it's obvious from the diagram that angle of incidence is greater than the angle of refraction. So for part A, we can write that angle of refraction is less than angle of incidence. That means that the light is bending towards the normal in medium B. So we can say that a light is bending towards normal in medium B. And we know that when light goes from rarer to denser medium, if this is a rarer and this is a denser medium, the light bend towards the normal. So here the light is bending towards the normal in medium B, so that means the medium B is denser. So we can say that the medium B is optically denser. Not say it's denser, we will say it's optically denser. Because when light goes from rarer to denser, it bends towards the normal. So this is bending towards the normal because angle of refraction is smaller than angle of incidence. So we have justified our answer as well B. If the speed of light in medium A, so this is the speed of light in medium A, which is VA. Sorry, this is small a, and this is VB. This is speed of light in medium A. So what is the refractive index of B with respect to A? So we have to write the refractive index of B with respect to A. So how do we denote it? So refractive index of B with respect to A. So we write it as, this is written as NBA, or in some books you may find it as the mu sign refractive index of B with respect to A, and that is given by the speed of light in A divided by speed of light in B. So this is now refractive index is given by speed of light in medium A divided by speed of light in medium B. Right. So this is the refractive index of B with respect to medium A. Okay. Now moving on to the OR part. So we are attempting the OR part now, and it has also part A. Okay, a ray of light starting from diamond is incident on the interface separating diamond and water. Draw a labeled ray diagram to show the diffraction of light in this case. So ray of light is going from diamond to water. So let's say this is the surface that is separating the diamond and the water. And this part, this medium above is the diamond, and this medium below is the water. And now let's draw a normal to the surface, and this is the reflecting surface. I'm going to label it as, this is the reflecting surface. It's the surface that separates the diamond and the medium diamond and the water. So this is diamond. Okay, this is normal. Normal to the reflecting surface, because this is a normal. So I'm going to represent this as the dotted line. Okay. All right. Now the ray of light is coming from the diamond. So let this be the incident ray, and the angle between the incident ray and the normal, this one, is the angle of incidence. So this is angle of incidence, Now, water is optically rarer than diamond, so this is the incident ray. We are cutting the R section. This is the angle of incidence. Now, this is optically denser medium diamond, and water is optically rarer if we compare these two media. So that means that the incident light, when it goes from diamond to water, its speed of light increases here as compared to the speed of light in diamond. So that means it will move away from the normal. So I'm going to make it like this. So it moves away from the normal. So this is moving away from the normal. This is the refracted ray. So this one is the refracted ray. And this is the angle of refraction. So this is the angle of refraction. Okay, so this is how the ray diagram for refraction of light in this case looks like. Next is that absolute refractive index of diamond and water are respectively. We have to find the refractive index of water with respect to diamond. Okay. Now, absolute refractive index of a medium means what is absolute refractive index of a medium? So, absolute refractive index of a medium means that ratio of speed of light in air or vacuum to speed of light in that medium. So absolute refractive index of medium we denote it by n, and where m is the medium, this is absolute refractive index of medium. This is denoted by the speed of light in air or vacuum. So c is the speed of light in air or vacuum divided by the speed of light in that medium. So this is the absolute refractive index of medium, where c is the speed of light, v is the speed of light, and vm is the speed of light in that medium, and we call it the refractive index of that medium. Okay, now we have two mediums here. One is the diamond, and its refractive index is 2.4. So let's say this is diamond. Refractive index of diamond is speed of light in air or vacuum divided by the speed of light in diamond. And we have water, so absolute refractive index of, sorry, this is absolute refractive index of water, which is speed of light in air or vacuum divided by the speed of light in water. Now, absolute refractive index of diamond and water is given, which is 2.42 and 1.33. So this is 2.42, that is equal to C upon VD, and this is 1.33, which is equal to C upon VW. Okay, now what are we supposed to find out? We are supposed to find out the refractive index of water with respect to diamond. So let's find out. So refractive index of water with respect to diamonds. That means, so this will be the refractive speed of light in diamond divided by the speed of light in water. So we have to use this. This is the refractive index of water. So refractive index of water with respect to diamond. We have to find out. So diamond, so there is a refractive index of water with respect to diamond. And okay. So refractive index of water with respect to diamond, we have to find out, and it's noted by this. You write it as refractive index of water with respect to diamond, or refractive index of water with respect to diamond, which is divided by refractive index of diamond divided by refractive index of water. Sorry, speed of light in diamond to speed of light in water. So these are the two equations, one and two. And if I divide two with one, so let me divide two with one, which will give me. So if I divide two with one, which gives me it's 1.33 divided by 2.42, and this is c upon speed of light in water to c upon speed of light in diamond. Okay, so c and c gets cancelled. I'm left with 1 upon speed of light in water upon, this is divided by 1 upon speed of light in diamond. This becomes speed of light in diamond divided by speed of light in water. Okay, so this is Vd upon Vw is equal to 1.33 divided by 2.42. So this gets cancelled. We can remove the decimals because after the decimals we have same number of digits. So this is 133 by 240. So 133 divided by 240, which should give me, so 133 divided by 240. This is equal to 0.549. So this is 0.549, and I can round it off to two decimal places. This is 0.55. So 0.55 is the speed of light in diamond divided by the speed of light in water. And this is the refractive index of water with respect to diamond. So our answer is 0.55. So this is how you find out the refractive index of water with respect to diamond. So when you write refractive index of water with respect to diamond, so that means that this is how we write it. Refractive index of water with respect to diamond. So that means velocity of speed of light in diamond should be divided by velocity of speed in water. That gives you the refractive index of water with respect to diamond. And we have got that by dividing these two equations 2 by 1. So we got the ratio of speed of light in diamond to speed of light in water, which is 0.55. This is the refractive index of water with respect to diamond. Okay, for next question, which is question number 26, we have to state the rule to determine the direction of magnetic field produced around a straight current carrying conductor. So this is part A, and the rule is right hand thumb rule. So this is right hand thumb rule that is used to find the direction of magnetic field produced around a straight current carrying conductor. And it says that if we grasp, so we don't have to actually grasp. If you imagine that if we grasp a straight current carrying conductor in our right hand, so this is a straight current carrying conductor in our right hand, such that thumb points in the direction of the current, thumb points in the direction of current, then the direction in which the fingers curl gives the direction of the magnetic field. So this is the right hand thumb rule, and let's say if it's a straight current carrying conductor, and if the current is flowing in this direction, and if you use our right hand thumb rule, so this is our right hand, the thumb is pointing downwards, the fingers in which the fingers curved. So we know that for a straight current carrying conductor, the pattern of magnetic fields about any element, let's say this is the element, it's always concentric circles. So we have to give the direction, whether it's clockwise or anti-clockwise. And if you use a right hand thumb rule, so here the current is in downward direction. So if we like try to grasp the conductor in our right hand, the thumb points in the downward direction, the fingers are curling, they are going for into the page of the paper in this direction. So this is the direction of the magnetic field. So they are going into the paper, into the plane of paper. Okay. So you have to imagine this as the plane of the paper. So make sure you imagine this as the plane of the paper. So let this be the plane of the paper. And then you have to give the direction if it's into the plane of the paper or it's out of the plane of the paper. Okay, so let's move on to the B part. Now, the force experienced by a current carrying straight conductor placed in a magnetic field which is perpendicular to it. What is the rule that we use? And the rule that we use is Fleming's left hand rule. This is Fleming's left hand rule. So now it states that if we stretch, so if we stretch our forefinger and middle finger and thumb of our left hand, and that is mutually perpendicular to each other. Now we have to line our forefinger such that forefinger gives the direction of the magnetic field. So make sure you align the forefinger in the direction of the magnetic field, or you point the forefinger in the direction of the magnetic field. So such that forefinger gives the direction of magnetic field. And align your middle finger in the direction of the current so that the forefinger gives the direction of magnetic field. And we can say that, and middle finger is aligned or pointing in the direction of middle finger is pointing in the direction of the current. Okay, that is current. Then because your thumb forefinger and the middle finger are mutually perpendicular, they are stretched mutually perpendicular, then the direction in which the thumb points give the direction in which the thumb points gives the direction of the force acting on a conductor, gives the direction of force or the motion of the conductor. Direction of force acting on the conductor or the motion of the conductor gives the direction of force or the motion of the current carrying conductor. So this is the Fleming's left hand rule. That means you have to stretch your forefinger, central middle finger, and the thumb of your left hand mutually perpendicular to each other. So let's say this is the forefinger, which gives the direction of the magnetic field, which is B, and this is the middle finger or the central finger, which gives the direction of the current. Then this thumb, when it gives the direction of the force, and all these are mutually perpendicular to each other. This is Fleming's left hand rule. Very useful rule to find the direction of the force. So this is Fleming's left hand rule. Okay, moving on to the next question. Yeah, next question is question number 31, and it says that state the reasons for myopia and with the help of ray diagrams show the image formation by a myopic eye and then the correction of myopia using an appropriate lens. Okay, so first of all, what is myopia? And the other name for myopia is uh, it's the nearsightedness. That means we are able to see the nearby objects but not the far away objects. So this it is also called nearsightedness. And with this name, nearsightedness means able to see nearby objects but cannot see far away objects. It's not that you are not able to see far away objects. You're not able to see far away objects distinctly. Means they are dull, or maybe it's dimmed. They are dimmed. So you don't have to write that you altogether cannot see far away objects. You have to write that you cannot see far away objects distinctly. You are able to see, but if there are two objects, you may not able to distinguish between them. So it's not clearly you can see the far away objects. And this is because your far point is that is infinity. Far point is nearer than infinity. Let me show you how. So uh, your far point is nearer than the infinity. I will draw a ray diagram to show you that. And so myopia, as I told you, is also nearsightedness, and the person with myopia, he can see the nearby objects clearly, but cannot see distant objects distinctly. Now, a person with this defect has the far point nearer than infinity. Reason is that the far point is nearer than infinity. So far point I'm saying is you have to understand this. The far point is nearer than infinity, and then I will let you know what exactly you have to write as an answer. So far point is nearer than infinity. Now, infinity means that the far point means that the maximum distance up to which we can see an object, which is infinity. So here the far point is nearer than the infinity. So I'm going to draw a ray diagram. Let's say this is the eyeball. It may not have, okay, this is the eyeball and this is the eyelids, let's say. Okay, this is the islands and now, as I said that the far point is now nearer than the infinity. So, so in the question it's asked, we have to find the image formation by a myopic eye. So image formation by a myopic eye, I'm going to draw the image formation by a myopic eye. So here the as I told you that the far point is nearer than the infinity, so let there be rays of light coming from infinity. So these are the rays of light coming from the infinity, and lens is this lens, which is a sort of convex lens, is not able to converge them on the retina. Instead, it's converging them in front of the retina. So this is where the rays of light are converging in front of the retina, and the image is formed in front of the retina. take this off. Okay. So now this image is formed, and this is the retina. So image is formed in front of the retina. This is where the image is formed. And this is because the light rays coming from the infinity, they are meeting before the retina. So now this was supposed to be, so this is from where the light rays are coming. This is the far point. This is the far point. And now the far point has is nearer than the infinity. So this is at infinity, and the far point is now here. So that means the rays of light are not able to, I'm going to draw these as a daughter. Okay. Now the rays coming from the infinity, this lens is not able to convert them and focus them on the retina. Instead, they are intersecting before the retina and the image is formed here. So that means that the far point here, this is not the far point, this is the far point. And from here, the images, if from here, if this is the, that means this is the maximum distance up to which this eye can see and focus this image on the retina. So how are we going to correct this? So this is an image formation by a myopic eye. So I can write it here. This is the image formation by an myopic eye. So now this far point, which usually was here, now it has come nearer than the infinity. So it has moved here. So that means we have to correct this by using, so that means the rays of light coming from this point, far point, we have to make sure that they are focused on the retina. So for that, the corrective lens that we will use these rays of light to diverge more and then focus on the retina. So we are going to use the diverging lens, which is the concave lens. So let me show you how we are going to do that. And for that, let me copy this. Okay. So I'm going to put here the concave lens. So this is the concave lens. And now what this concave lens is going to do, this concave lens is going to divert these rays of light from here. So this is where the refraction is happening. And okay, from here, the rays of light will be diverged outwards. The rays of light will be diverged outwards. And I'm going to make this lens a bit bigger. Okay, now this is, let's say, the eye lens. So rays of light are now being diverged outwards. So that from this point, now the points from where they are being converged is nearer to the edges for the lens. So from here, these rays of light are now converged and brought back to focus on the retina. So this is how the convert divergence and then convergence is done, and the rays of light are now focused back on the retina, and this is where now the image is formed. This is not where the image is formed. Now the image is formed here on the retina. So this is where the image is formed. Okay, so this was the image formation by a myopic eye, and this is the correction. by the myopic eye. So this is the correction of myopia. You can say this is the correction of myopia. So now your far point has now moved back to the normal far point, which was at infinity. So all the rays coming from infinity are now diverged and then converged by this, diverged by the concave lens and then converge to bring them on the retina. So this is the correction of the myopia. And instead here you can also draw the lines. Just make sure that all the rays coming from here. So your far point is here. It will convert those rays of light, and so now all the rays of light coming from infinity will be converged at retina, and all the rays coming from your the myopic far point will also be converged at the retina. So this is the correction of myopia. So correction of myopia using an appropriate lens, which is the concave lens. So this is the concave lens. So what you have to write? So you have to state reasons for myopia. And okay, we have forgot to state the reasons for the myopia. The reasons for myopia could be the excessive curvature of eyelids. And I forget to write the reasons for myopia, which could be the excessive curvature of eyelids. That means that the eyelids, excessive curvature of eyelids. This could be one of the reason. And the other reason could be elongation of the eyeball. Eyeball has elongated and the image is now forming in front of the retina. So elongation of eyeball. These are the reasons for myopia, and this can be corrected using a concave lens of appropriate focal length. Okay, for next question, it's what is a solenoid and when does a solenoid behave as a magnet? So let's write down the definition of the solenoid first. And so solenoid, this is, so it is a coil of insulated copper wire, it's coil of, we can say, many turns. So it is a coil of many turns wrapped, many turns of insulated copper wire wrapped closely in the shape of a cylinder. That is solenoid. Okay, when does a solenoid behave as a magnet? Solenoid behaves as a magnet when current is passed through it. So we can say that it behaves as a magnet when current is passed through it. So that's why we also call it electromagnet. So when current is passed through it. So this is the solenoid. Now we have to draw the pattern of the magnetic field produced inside it, showing the direction of the magnetic field lines. So let's draw a solenoid first, which is a coil of many turns wrapped closely in of insulated copper wire wrapped closely in the form of a cylinder. So these are coil of many turns, and these turns are very close, very close of insulated copper wire and it takes the form of a cylinder. So this is the solenoid. And we have to show the direction of the magnetic field lines. So let's connect it to a battery so that the current is passed through it. So the current is flowing in this direction. So this is the direction of the current and magnetic field lines. So inside solenoid, the magnetic field lines are equidistant parallel set of arrows. So these are the equidistant parallel set of arrows inside and outside. They are closed curves. So this is the closed curve. These are the magnetic field lines. And you see that they are emerging from one end and merging at the other end. So it's going out, it's coming in. So this is, so let's say these are emerging from this end. So this is the direction and emerging at this end. So emerging at this end and merging at this end. So emerging, emerging, and merging. So this is north where the magnetic field lines are emerging. This is south where the magnetic field lines emerge. Okay. So inside the direction of magnetic field lines is from south to north. So inside solenoid, direction of magnetic field lines is from south to north. And outside solenoid, the direction of magnetic field lines is from north to south. And what I'm writing is the direction of magnetic field lines for solenoid. Okay, so inside is from south to north and outside is from north to south. So this is the pattern of magnetic field lines. Pattern of magnetic field line produced inside it showing the direction of the magnetic field line. So inside it's from south to north, which is a uniform magnetic field. Okay, for question number 36, the first part is what is meant by the resistance of a conductor and we have to define its SI unit. So this is question number 36, first part of part A. And what is meant by resistance? The resistance of a conductor is the property of a conductor to resist the flow of charges. So we can say that it is the property of a conductor to resist flow of charges. It is denoted by R. And we know that V is equal to IR. So R is equal to V by I according to the Ohm's law. And we have to define its SI unit. So its SI unit is ohm, which has symbol like this. And we have to define 1 ohm. So 1 ohm is 1 volt by 1 ampere. And we can say that, so definition of 1 ohm is, we can say the resistance is said to be 1 ohm, or resistance of a conductor is said to be is said to be 1 ohm, when it has a potential difference, has a potential difference of 1 volt and current of 1 ampere flows through it. This is current of 1 ampere flows through it. Okay, so this is 1 ohm. So 1 ohm. Now list two factors on which the resistance of a rectangular component conductor depends. So resistance of a conductor depends on the length of the conductor, the area of cross section of the conductor, because we have to mention only two factors. So I'm going to write the length of the conductor and the area of cross section of the conductor. So length of conductor and area of cross section of conductor. So I can also write that area of cross section of conductor, and we can say the resistance is directly proportional to L, and the resistance is inversely proportional to the area of cross section of the conductor. So these are the two factors. Okay, now the next part is how will the resistance of a wire be affected if its length is doubled and radius is also. First one, length is doubled. How is the resistance affected? So this is the third part, and we know the resistance of a conductor is given by rho into L by A. Let this be our first equation. Now new length is 2 times L. The length is doubled. So length is doubled means that the new resistance is rho into 2L dash. So let's write the new length, which is L dash by A. So this is L dash by A, and new length L dash is 2L. So let's take 2 out. So this becomes 2 into rho into L by A, which is 2 times R. So resistance becomes 2 times. So we can say when the length is doubled, resistance becomes 2 times. Okay, now the second is when the length is doubled and radius is also doubled. Okay, this was the first one, first part. And it's given that length is doubled and radius is also doubled. So radius is also doubled means it's written also. So also means that the length is also taken into consideration. So our formula for resistance is rho into L by A. Now new length is 2L and the new radius is 2R. And our new resistance will be rho L dash, and area of cross section is pi R square, which becomes pi R dash square. So length is now 2L, pi R dash is 2R the whole square. So rho into 2L, pi into 4R square. So this gets cancelled too. So that means new resistance is, this is rho L, and this is 2 pi R square. Then pi R square is A. So this is half of rho L by A. Rho L by A was our original resistance. So new resistance becomes half. Resistance will reduce to half. So we can say that new resistance will be half of original one. So new resistance is half of original value. Okay. Moving on to the OR part, it's given that in an electric circuit, three bulbs of 10 watt each are connected in series to a source. An inner circuit set of three bulbs of the same voltage are connected in parallel to the same source. So let's visualize what is given to us for the OR part. So this is the OR part. So there is one circuit where a set of three bulbs are connected in series. So let this be one bulb, this be the second one, and this be the third one. So these are connected end to end, and we know that when they are connected end to end, the effective resistance increases. We have to keep that in mind. And so these are of 100 watt each connected to one source. So these are of 100 watt each, and they are connected to one source. Okay, inner circuit set of three volts of the same voltage connected in parallel to the same source. Okay, let's say they are connected to a battery of voltage V. Okay, now in another circuit they are connected in parallel. So this is they are connected in parallel. So what do you mean by parallel? Parallel means that the one end of all the bulbs are connected to one end of the battery, and so this one end of all the bulbs is connected to one end of the battery. It's same source. So V remains V. So one end of all bulbs is connected to one end of the battery, and the other end of all bulbs is connected to other end of the battery. So this is the series circuit, and this is the parallel circuit. Okay. Now this is the all part. Okay. Will the bulb in two circuits glow with same brightness? Justify your answer. Okay, as I told you here, the effective resistance of these bulbs increases as they are connected in series. In second one, as they are connected in parallel, so effective resistance decreases. So we can say that the answer for that is no. They will not move with same brightness, and the reason is that in series combination, overall resistance will increase. So overall resistance will increase, and hence it will decrease the current. So that means if it decreases the current, then potential difference also divides. So potential difference also divides, therefore power consumption is less by each one. And glows, and hence they will glow, and hence they will glow with less brightness. Okay, but in parallel, uh, it will not be the case. So for parallel circuit, you can write that in parallel combination, overall resistance will decrease and hence increasing the current. So potential difference is the same. However, the potential difference in that the parallel remains the same. So therefore, power consumption is more, and each bulb by each bulb, and hence they will grow with more brightness. So here the brightness is less. And now let one bulb in both the circuits gets fused. Will the rest of the bulbs continue to glow in each circuit? Give reason here for your answer. So the rest of the bulbs will not glow in series, but will continue to glow in the parallel. So we can say that in parallel combination, each bulb will get okay, let's write down for this one, let's write down for the parallel as well. So this was for the series combination, and for parallel combination, you can write that in parallel combination, each bulb will get the required potential difference. So we can say that in parallel combination, each bulb will get the required potential difference. Hence, the required current. So they will get the required potential difference, and hence they will get the adequate current, and hence they will glow with, we cannot say the more brightness, but the normal brightness. Hence, so as compared to the series, it's more brightness, but they will glow with more brightness as compared to the bulbs in series combination. Now let's try to answer the other part. The other part says that now let one bulb in both the circuits get fused with the rest of the bulbs continue to glow in each circuit. No, it will not glow in the series because they are connected end to end. So none of the bulb, not even the fused one, not even the bulb that is broken, but none of the bulbs glows in series combination. As the circuit gets broken and the current, it stops flowing. But in parallel combination, in series none of the bulb will glow. And in parallel combination, the only the broken one will not glow, but other bulbs will continue to glow. So we can say that in parallel combination, the other will glow with same brightness because the same voltage is available to them. And this is because the potential difference across each device in a circuit in parallel combination is same. So same voltage is available to them. So in parallel combination, the other two bulbs will glow with the same brightness. So this is the answer for this one. Let's move on to the next question. Okay, for question number 39, a student took three concave mirrors of different focal lengths, and these are the concave mirrors of three different focal lengths. And he performed the experiment to see the image formation by placing an object at different distances with these mirrors. We have to answer the following questions. This is the object distance, and we know that the object is noted by U, if focal length is noted by F. So list two properties of the image formed in case one. So let's consider the case one, which is a concave mirror. So we all know that concave mirror has the reflecting surface curved inwards. Let's say this is the pole, and this is the center of curvature, and this is the focal length. And it's given the focal length is 20 centimeters. So that focal length is the distance between the pole and the principal focus, which is 20 centimeter. Let this be the non-reflecting surface. This is a concave mirror. Okay, now it's given that the object distance is 45 centimeter. So object distance is u. So double of the focal length is the radius of curvature. So this is the radius of curvature, which is double of the focal length. So this distance is 40 centimeter because it's 2f, which is the radius of curvature. So distance between the pole and the center of curvature is the radius of curvature, but the object is placed at 45 centimeters. So it's beyond center of curvature. So this is where the object is placed. So object is placed here. Okay, if we try to draw a ray diagram, or if you remember the ray diagram for this one. So ray diagram for this one. So this is the object distance, which is U, which is 45 centimeter. Now the ray passing going parallel to the principal axis will be coming out of the principal focus like this. And these are the directions. So we have to consider one more ray to complete to get the image, and let's take the ray of light going through the principal focus that will be coming out after reflection from the concave mirror. It will be coming parallel to the principal axis. So this is what it looks like. Okay, and these rays are actually meeting here. So that means the image is formed here, which is inverted. So the image, so this is the object AB, and this is the image A dash B dash. So now let's read out the question and try to answer the question and try to answer it. Okay. So the object was beyond the center of curvature for the concave mirror. So the image is formed between C and F, and the image formed we have to. So the object was beyond the center of curvature, and the image is formed between center of curvature and focus, which is inverted and real. So this is the image form, which is formed by the actual intersection of the rays, which is inverted and real. And list two properties of the image formed in case. So two properties of the image formed in this case is image. Let's write down the nature. So I'm going to write down the nature of the image. So image is real and inverted. And also if we have to write down the position of the image, let's write down two properties. Let's write down the position of the image, which is between C and F. So you can take the help of this diagram. It's not necessary to draw the diagram. You just have to remember how exactly it looks like and just give the nature, the two properties. So I've listed the two properties of the image in this case. And the two properties that I have listed here is real inverted, and if you have to write also the size of the image, so this is smaller than the size of the object, so we can write that it's diminished. Okay, so these are the properties of the image formed. Now, in which of one of the cases given in the table, the mirror will form real image of same size and width? So we know that image size and object size is same when the object and image are formed at the center of curvature. And center of curvature means the distance from the pole to the center of curvature means it's the radius of curvature, which is twice the focal length. So twice the focal length. Here the focal length is 15 and object distance is 30. So this object is placed at center of curvature. So this is the case 2. So we can write that for B, it's the case 2, and I will show you how. So case 2, because the focal length, because here we can write the focal length is 15 centimeter and object distance is 30 centimeter, which is twice the focal length. Twice the focal length is the radius of curvature. So that means object is at, so position of object is at C. So when object is at C, which is 30 centimeter here, so image is also formed at C, which is 30 centimeter. And both the image distance and object distance. So image distance and object distance are 30 centimeter. And we know that the magnification is given by V by U. So it comes out to be 30 by 30. It's a negative U, V by U, and both are negative here. This is also negative. This is also negative. So this is negative, and there is one more negative of the formula. So this comes out to be negative 1. So magnification comes out to be negative 1. So if you use this, so this is negative, negative 30, negative 30, this is negative 1. And magnification is negative 1. So negative means inverted, and 1. 1 means that the image size is equal to object size. I will also show you how. So image size is equal to object size. So let's copy this. So I'm going to place the object at center of curvature. Let me place the object at center of curvature. This is the object, and this is the ray of light that's going parallel to the principal axis. It will be going through the focus. So rough diagram. Okay. So it will go through the focus. And another ray of light that passes through the focus will come parallel. Okay. So this will come parallel to the principal axis, and they will meet at a point. So let's say they meet here. Okay, let this be the principal focus. This is the object AB, and this is the image A dash B dash, which is inverted. These are the direction of the rays of light. So object is at C and image is also at C, and the object size is equal to the image size. This is how the image is formed when the size of the image and object size is same. So both are formed at center of curvature and their sizes are equal. Name the type of mirror used by the dentist. So the type of mirror used by the dentist is also a concave mirror. So dentists use concave mirror to see the enlarged view of the, so dentist, they use concave mirrors because concave mirrors, they forms not only the enlarged but the erect image, because we can say that the concave mirrors, they form not only magnified or enlarged but erect image. The enlarged image when object is very close to the mirror. Okay, now let's move on to the or part. This is the or part. Look at the table and identify the situation. That is the object distance and focal length, which resembles the situation in which concave mirrors are used as shaving mirrors. So that means that the object should be very close to the pole and it should have the minimum object distance. So that's the case 3. The object is placed between the focal length and object is placed between the focus and the optical center. Here the focal length is 30 centimeter and object distance is 20. So that means this is within the focal length. Here the object. Okay, look at the table identified situation means we have to relate the object distance and the focal length, which is the situation in which concave mirrors are used as shaving mirrors. For shaving mirrors, we should see the enlarged image of the face to get a close shave. So enlarged image is formed only when the object is distance is within the range of the focal length. So here the focal length is 20, object distance is, so u is greater than FAL. So this cannot be the case. So here also the object distance is greater than the focal length. This cannot be the case because object has to be within the focal length. So in this case, the object distance is less than the focal length. So this is the case, the third one. So third one should be the ideal case for which resembles situation in which concave mirrors are used as shaving mirrors. We have to draw a ray diagram to show the image formation in this case. So let's draw a ray diagram where the object is placed between focus and the pole of the mirror. So this is, let's say, pole. This is the non-reflecting surface, and the line which passes through the pole and the center of curvature is the principal axis. Let's say this is the focus and this is the center of curvature. So this is the focus. Now the object is placed between the focus and the principal pole of the mirror. So this is how the where the object is placed. So and the object is denoted as AB. Now the ray of light that goes parallel to the principal axis will come out of the focus, out of the principal focus, or will go through the principal focus. To be more precise, and the ray of light which is incident at the pole will follow the laws of reflection and will be reflected using following the laws of reflection. Thus, that means the angle of incidence here is the angle of reflection. So this is the incident ray, this is the incident ray, and this is the reflected ray. So angle of incidence is equal to angle of refraction here, and the normal is the principal axis. Okay. So obviously here these rays will not intersect, but if we produce them backwards, so if we produce them backwards, so produce them backwards, so these are not the actual rays, but we are assuming them to be in the backward direction. So I'm going to get a dotted line for this and this one also. Here the rays of light are assumed to be intersecting here. So this is where the image is formed, and you can see that it's enlarged and erect. So this is virtual and erect and enlarged. So this is how the this is the ray diagram to show the image formation which resembles the situation in which concave mirrors are used as shading mirrors. So object should be close to the mirror, concave mirror, that is between the focus and the pole of the mirror. So this is case three. So we have to write that. You have to also mention which is the case. So this is case three. Case three means this is the one. And I may get some comments that they are not able to understand and this situation. So to understand this situation, you should have thorough knowledge of the chapter. If you don't know what is U, what is F, what is U, what is F, then you may end up commenting on this video that it's the worst explanation ever. So kindly go through the chapter first and then come to these questions, because these are the you are supposed to answer these questions only when you have the thorough knowledge of the chapter, else it will be going over your head. So with this, we are done with this part and the final set of 2023, which was 3161 paper code. Do like, share, and subscribe. Thank you for watching.